All right, good evening everyone, and welcome to the March meeting of the Royal Astronomical Society of Canada, Ottawa Centre. I think I've misplaced my clicker. There it is. We've got a fantastic program for you tonight. We've shuffled the order of things a little bit, but we'll be starting off with Dave Chisholm and Clear Skies. Then we'll be doing our observation reports. Right after that, Sharon Odell will join us to give us an update on the Dominion Observatory and the challenges it's facing with the expansion of the civic campus of the Ottawa Hospital. Then we'll go to break, and then we'll have our guest speaker tonight, Dr. Matt Kaplan, giving us his talk titled The Inner Lives of Dead Stars, followed by announcements, closing remarks, and everyone's favorite door prizes. So we'll start off with members in the news. Dr. Janet Tulloch has won the Royal Astronomical Society of Canada's sesquicentennial year contest, Imaging the Skies, for her piece named Twilight of the Gods in the Creative Works Experience level category. Congratulations, Janet. Don't think I've seen her, but I'm sure she's here in spirit with us, and she'll probably catch the recording at a later time. In the March calendar, the March RASC Observers calendar, Mike Worth's photo of Montes Alpes in that general area was featured. And interestingly enough, there is the Lunar Challenge from last month, the Alpine Valley Rail. So thanks, Mike, for having submitted that to the Society's calendar, and congratulations on nabbing the observing challenge there. All right, our new members last month, there they are, Jongwon Ao and Melvin Harris. Welcome, and hope you'll enjoy being a member of the club. And thus far, we have 18 new members in 2019. All right, and I'm going to hand the reins over to Mr. Dave Chisholm.
Great, thank you. Okay, so let's take a look at the Ottawa skies for this month. So the full moon is on March the 21st. This full moon has a variety of different names. It's known as the full worm moon, the crow moon, the full crest moon, and the Lenten moon. And this is the last of the supermoons for 2019. Daylight saving time resumes on March the 10th. And you'll notice on today's date there's a little dragon on there. I don't know if any of you know what type of dragon that is. Welsh, that's correct. Today is St. David's Day. I'm named after St. David because of my Welsh background. And as they say in Wales, Cymru am byth, Wales forever. Oops, I hit the wrong button.
Here, let me fix that for you. There you go.
Thank you. Okay, so I've just got one comet this month, and the Schwarzmann-Walkman, it's going to disappear behind the sun mid-month, but for the first part of the month it should be visible. In terms of the planets this month, Mercury is not visible. Venus is visible in the early morning. Mars is visible in the first part of the evening. Jupiter is visible just before sunrise. Saturn is visible also just before sunrise. Uranus is visible all night, and Neptune is not visible this month. And there is your cartoon of the month. Thank you.
I have a feeling my wife felt this way at some point in time. All right. So I'm going to welcome Rick Wagner up to talk to this one here. Rick? Don't fall down the stairs, though. I forgot that I'd put these slides in this particular spot.
So, evening, thanks. Many of you will know that in addition to being an Ottawa Centre member, I'm also a Kingston Centre member, and in fact, for my sins, I'm the president of Kingston Centre. So we're doing a little fundraiser for which I have tickets if anybody would like to buy them. What we've done is we've put together a little package for sort of the beginning astronomer, a copy of the latest edition of Night Watch by Terry Dickinson, the jumbo edition of the Pocket Sky Atlas. Why they call it Pocket anymore, I don't know, but it's a lovely little atlas. The Binocular Highlights book by Gary Saronic, now the editor of Sky News. A planisphere, so you can figure out what's up when. And a pair of 20 by 80 Celestron binoculars. The mouse is just in there for scale, so you can see they're big. And also a tripod to put them on. So I will have tickets. I don't even know what the price is. They're $2 each or 3 for $5. That's what I thought. So if anybody'd like see me during the break or after the meeting and help support the Kingston Centre in getting up enough money to buy an observatory site. Thank you.
Thank you, Rick. And getting enough money to buy an observing site or an observatory site certainly sounds like a worthwhile cause, and one that... All right. All right, so we're going to dive right into observation reports. Here's our list of observers tonight. So if you're on this list, you just queue up on the right, and we'll get that process going. And Jim, you're up first.
Lots of pressure.
No pressure.
No pressure. It's the green button to advance.
Green is laser, this button to advance, the one on the right.
All right, thanks. All right, so despite all the lovely cloudy weather we've had, I have got out a few times over the past couple of months, both during the day and in the evening. We'll start with some solar observing. So if you have been squirreled away in your house, hiding from the bad weather, and you're thinking you missed something on the sun over the last 2 months, well, you haven't missed anything. It is about as featureless as you can imagine. So hopefully this is the minimum of the minimum, and it's all uphill for activity from here, but we'll see. Next was on the 9th, I believe, of February. We got a clear night, and as it had been quite a while since I had done any deep sky observing from my backyard, I put 2 refractors on at the same time with 2 different cameras. A color camera on the 4-inch scope, and a black and white on the 2.5-inch scope. That's on the right. H-alpha filter on the black and white scope, and then just a dual band color filter on the left. So as you may have guessed, this is the Orion Nebula. And I especially like this object because it has such a wide dynamic range, and there's a lot of detail in it. You can observe it at many different magnifications and always see something new. This particular night, the dust in between the running man up here and the main Orion Nebula started to come out, which was really neat to see. Kind of gives you an idea that this whole area in Orion is just all dust. It's one huge molecular cloud, and the nebulas we see are just little tiny spots where stars are being created. So that was a neat shot.
Jim, can you point out with the stars kind of why it's called the Running Man?
The Running Man, yeah. From my backyard, it's not easy to see the reflection component, but there's a little bit of the blue. So if you look, this man is on his side. Here are his legs. It's one arm here and one arm there, and his head's up here somewhere, and he's kind of in a pose like this. Under a dark sky, it's much easier to see. H-alpha, you can't really see it as well because the reflection component isn't visible. Only the H-alpha component is visible. So that's about as good as I can get from my backyard in Alta Vista. That's about just over 6 minutes of stacking 10-second exposures. Next, moving north up through Orion, I stopped off at the Horsehead and the Flame, another perennial favorite. I especially liked the H-alpha shot because it really brought out the extent of the emission nebula, IC 434, up here off to the east side. Thought that was pretty neat. Even further north in Orion, up near his club, I guess, is the monkey's head. I don't know if you can make out the shape of the monkey. This is his forehead. He has an ear here. His eye, his mouth. It's like a Curious George in profile. I don't know if you can see that. So that's another fun target to view. It's nice because it's up very high right now. It's probably better than 60 degrees up, so it makes it a good target for in the city. Next, I tried to get the Cone Nebula, Foxfur, and the Christmas tree, and these are very, very difficult to get from in the city. With the color camera, there was just too much light pollution to really pick anything out. You can kind of see the cone up here at the top. The Christmas tree cluster you can see, of course, but the rest of the Foxfur Nebula, it was really difficult to see. So the H-alpha is really necessary to see this nebula from in the city. And I thought it was neat how the dark nebula over here really popped out in the H-alpha. That was kind of neat. And then my last deep sky object was one of the observing challenges for the month of February, the Rosette Nebula, which is actually 4 different NGC numbers plus the cluster itself. This is a really fascinating target as well. Lots of things going on. We have some shock fronts here where the young stars are pushing away the gas. Some more up here, the sharp lines. You see, that's a shock front, and then some globules still remaining, denser, colder material that's resisting the solar winds, and maybe will eventually form new stars. So that was I was happy with that shot. Now that was quite a bit longer total exposure than the others, about 25 minutes, mainly because I walked away from my scope and put my kids to bed, kind of forgot that it was running, and came back and went, oh, it's still tracking, all right. Save. So that was it for the deep sky for the last 2 months for me. The last thing to look at is the Lunar Observing Challenge. I'm jealous of Mike Worth's picture, by the way. He must have excellent skies. But just to zoom in and get an idea of what we're looking at, this is from the Lunar Orbiter, number 4, which was in orbit around the Moon between May and July of 1967 in preparation for the Apollo missions. And you can see the rill itself is not very big. It's less than a kilometer wide all along its length, and it's only 100 meters-ish deep at the deepest. So this is actually a very challenging feature to see on the Moon. I know because I've tried to image it for the last 5 years with very little luck. So this is from September of 2013. Maybe it's there, maybe not. January 2014, yeah, maybe a hint of something there, but I don't know, not quite. March 2014, this is light from a different direction. It's kind of there, but it's hard to say. September 2015, yeah, no, didn't catch it then. And these are actually the best shots. I have like a lot more shots. These are the best ones. April 2016, yeah, it's kind of there. You can kind of see some of it in here, along here. So it's getting better. And all through this time period, my equipment is getting better. I'm refining my methodology. So that's going along with the improvement in the quality of the images. And then most recently, April 2018, yeah, kinda. It's kinda there. If you didn't know that there was something there, you might say that it was an artifact of the sharpening process, but in this case, I would argue that I did catch the real, but not that clearly. But anyway, that's the best I can manage for now. Thank you.
Thanks, Jim, and thanks for pursuing some of the observing challenges. All right. Oh, Taras, you're next. Sorry about that.
First, I want to correct myself regarding my explanation of the bluish tint of the moon in the eclipse picture I've shown the last meeting. Apparently, this one. Try to. Thanks. So essentially, I was wrong about the bluish tint. It's not a result of dispersion, but light scattering, rather. Thanks, Majid, for pointing it out, and I've learned from the links you sent. Thank you. And now to the picture. So Orion. Orion is my favorite constellation for many reasons. Was one of the first recognizable pattern I saw in the skies as a kid. Back then, it looked to me like something unnatural and mysterious, a collection of bright stars shedding their steady, vivid light, immovable as it seemed to me and majestic. There must have been mystery behind it. This picture of Orion.
Try it.
This one?
Just try that.
This picture of Orion was taken by me in late October a few years ago in Morris Island Conservation Area near Fitzroy Provincial Park, while the overlaid image is the illustration taken from Celestial Atlas by British author Alexander Jamieson. So I just took a picture of the Orion itself, and wait a second. Oh, I think I'm going in the wrong direction.
Need to go back?
Yeah.
Just do it from here.
Maybe not. How far back? This
One more.
One more. There you go.
Thank you. Which one's this one?
That one's back, and that one's forward.
So you can see the main stars: Betelgeuse, Bellatrix, the Belt, and Rigel here, a little bit of Orion's sword. And the illustration perfectly matches these stars, so it's precisely made. So I decided to combine it to show what the actual imagination of Orion, what it would look like, was for the time when Atlas was composed. Not sure if it works. Oh, there you go. So when we take longer exposures, then some details in the constellations show up. If our eyes could accumulate light the way digital cameras do, we would be able to see more than just stars and a faint nebulosity in its belt. This image was taken from the observation pad at FLO Observatory, so you can recognize the tree line. Oops. Sorry about that.
That's fine. There you go.
One more.
One more.
And if I need to navigate, it's this one here.
I don't know if that'll work or not, but that one's forward, that one's back.
Thanks. So So the more details show up in a longer exposure, which is the Barnard's loop, which is the remnants of supernova, which exploded a long time ago. It measures about 300 arc seconds. It's a huge part of a molecular cloud, which combines also this Lambda Orionis ring, part of the same cloud, as well as well-known little flame nebula here, and Horsehead Nebula and the Great Orion Nebula. So all those regions are rich in hydrogen, which glows in light of stars nearby. You can see it better here on this picture, which I took during Winter Star Party in Florida. The Betelgeuse, the very same Rosette Nebula. This is a strip of Milky Way going this way. Sirius, the brightest star, and of course, a great Orion Nebula over here with the tiny Running Man, and again, the flame and the horse head. And another close-up just to show some more details. In particular, the Flame Nebula shows up a little bit better. So essentially, this shows you more or less all the pictures which Jim showed you before, where they're actually located, for those of you who didn't have a chance to take a look at them yet. So for these two guys, just next to this bright star called Alnitak, Horsehead is a little bit below, and Flame Nebula just above it. While Orion Nebula, everyone knows it's really bright, it's part of the SOAR, it can be seen with the naked eye. So when we zoom in on Orion Nebula, well, it's a beautiful object, it's never gets bored to look at it. There is lots of things which always are there for you to discover, to find out what actually is happening, because this is a region where lots of new stars are being born, and well, we talk stars being born, but what actually happens? What does it look like? And by the way, there's also the Running Man Nebula with a little bit of nebulosity. So this region here, known as Trapezium, I tried to image it with a planetary camera, or actually I tried narrowband imaging first time in my life to see what it's going to be like. And I've got some details which would not show up regularly at a higher magnification. So you can see the trapezium and all the 6 stars. And because it's narrow band, so the oxygen shows blue, hydrogen green, and sulfur red. So you can see that definitely stars are red, but there is some objects which are not really completely red, although they look like small clumps, not red at all, rather. So those are clumps of matter. Something else is happening here as well. There was a tiny little red dot, so I got curious what it is, and I read about it. So next time I had a chance to image it again was again at the Florida winter party, where the seeing conditions were much better. Better to the extent that actually stars would produce diffraction rings around them. So the seeing was so steady, so stable that the diffraction rings around the stars were seen, as well as those objects that I was interested in that are right here. And you can see clearly that except for just regular gases, there is something going on here, which, if you Google the details, you'll see, well, the regions with denser hydrogen content and a new star inside it, newborn star, are called the proplates or protoplanetary disks. So this is one of them. There's actually quite a few more here, like this one here, but this is the brightest one and the largest one. So the gases and dust create this cloud around the star, which turns later into a accretion disk, which under the influence of the star's bright ultraviolet light and energy is later on turned into mostly dust, because the gas has been pushed in quite a complicated process called photoevaporation. But when this protoplanetary disk later on turns into accretion disk, then there is a clumps of matter which form in it, and that forms a planet or planetesimals, and later on the planets like ours just absorb all the matter around and turn into round spheres circulating the star. This is another, so this picture was from Hubble telescope. I just used it for the illustrations, as well as this one. So this is so-called Heroherbic objects, which are the clouds of gas as well, but the neighboring star emits, when it emits a jets of strong, powerful wind, it pushes these clouds so that they form this shape which sometimes has an impression that it's like a waterfalls or something which is pushing gases away from the stars. They're also common in the regions where the new stars are born. I tried to add more details as possible, so this might be a little bit overdone, but I think it still gives you an idea what they look like. Thank you very much.
All right, thanks, Taras. Next, we've got Andrew.
Thank you. And Mike? It's right there. You can speak into the podium if you like. Okay. Can you hear me? All right. So I took this image back in December, but to be frank, all our winters looked like this. At the time, I was captivated by this 22-degree halo, which is caused by ice particles in the air. While I was setting up my new Star Adventurer mount to try and capture Comet 46P weird tannin. Now, I decided to present this one for some context, because so Orion was down here, the Pleiades were up here, and Auriga around here. The comet of interest, somewhere there in the muck. It did clear up a little bit, but it proved to be an exceedingly difficult set of data to process, but I did manage to pull this out of it. There you go. So, of course, there's quite a bit going on in this image. The comet of interest, some dark nebulosity, the Pleiades, of course, and the California Nebula actually managed to show up. But I'll tell you, I spent a good 2 months working on this, because I had a strong gradient of the moon shining in from the side here. But I'm quite happy with how it worked out. It's the first time I used the Star Adventurer. I was using a Canon 70 to 200 millimeter f2.4 lens, a fairly large lens, and no guiding, 90-second exposures, so it turned out pretty well. And then, so fast forward to just last weekend, given these conditions we've experienced, I haven't been able to do much until last Friday. You just gotta wait for the text to disappear. It's on a timer.
Got it.
You do it here.
All right. Thank you, Brian. So this is what I encountered last Friday at FLO. According to the logs, nobody had been on site for at least a month, and of course, in the meantime, we had record-breaking snowfall. So I cleared all this for everyone. Thank you. That was a good, like 25, 30 inches of snow there. Now, during the months that I've been inactive, I've been making some improvements and adjustments to my equipment. This is my latest acquisition, a 8-inch Echeverri telescope. It used to belong to Rock Malin. He gave it to me, or sold it to me last year. So this evening was primarily about testing my equipment, and in particular the collimation of this instrument. And if anyone is familiar with Echeverri optics, due to their design with
two hyperbolic mirrors, they are not at all forgiving to miscollimation or misalignments, or even the interspatial distance between the mirrors. And I've had to come up with my own techniques, and I haven't had an opportunity until now to really see how well they worked out. And happy to say I'm very pleased with the results. It's not a pretty image, but it tells me an awful lot about the collimation tests. I was specifically looking for like the FWHM, the size of the star, it's the light spread of the star. I'm looking for the shape, on-axis coma and off-axis aberrations. And well, the only thing that is still present in this image is very slight spherical aberration. And that is caused actually by the distance between the primary and the secondary mirror being slightly off. And with this image, I was able to measure the true focal length that it was taken at. It was 1,607 millimeters, whereas the specification for this telescope is supposed to be 1,624. That tells me that the distance is a little bit off. Furthermore, the back focus position has a standard, and I measure that to be, where'd it go?
You hit the, you must have advanced the slide.
Oh, okay, spoiler.
Let's go back.
Yeah. Oh my,
Wrong way?
I guess.
You gotta hit the button on the left.
I was. All right. Oh. Okay. So doing a little bit of math and also comparing with other telescopes and their images on Astrobin, I was able to determine how much of an error I still had in that distance, and it turned out to be 0.3 millimeters. So I've since made that correction, and I'm looking forward to testing it again. But otherwise, the actual collimation of the alignments of the two mirrors, which is a really tricky thing to work out, is showing a great deal of promise. And it doesn't require any lasers or really expensive tools, just a really intricate setup with camera pointing into the telescope and looking for reflections and concentricity in the optical elements within. And the Hubble, incidentally, shares the same design as it's a Richard Critchay, and as I'm sure many of you are aware, they had issues. Yeah. So the moon was out that night as well, which is also another reason I took an open cluster. That was M33. But the particular colors that I was able to draw out in this image are what I wanted to showcase here. The regolith of the basalts and volcanic features and the impact spray provides quite some stark contrast. So I'm very happy with this image shot, lunar shot. And not that it was a particular focus, the lunar challenge just kind of showed up a little bit there. So I decided to point that out as well. Okay, thank you very much.
Great, thank you, Andrew. All right, Hugo?
Okay, the other night when I looked out my window at dusk, there was not a cloud in the sky, and I saw this alien spaceship. Now, I'm sure that those who watch Ancient Aliens will have your own theories as to what it is, but for the rest of us, I'll leave it to you to figure out what conditions could have caused that object, because that's not a normal kind of cloud formation that you would get. Anyway, I'll leave it up to you.
SR-71?
It is an unretouched photo.
All right. Thank you. Up next, we've got Jim Sophia. Advance the slide.
Okay. Well, we're going to be looking at the Lunar Challenge again, which is the Alpine Valley Rill. And the Alpine Valley, which is located right over here, is a lava, full of lava and lava flooded. And it is located east of the crater Plato, and it's between Mare Imbrium and Vigoris. And the Alpine Valley is bisected by this rill or channel, which measures 160 kilometers long by 8 kilometers wide. And I'll show you another shot I took from a different angle. Oh, I guess you didn't get the second one, huh?
no, I only got one image from you.
You only got one, okay. All right, yeah. I took this image with my iPhone connected to a Telview eyepiece in a 120 millimeter refractor. Thank you.
Thank you, Jim. Oh, am I stuck here? There we go. All right, Rick Wagner, you're up next.
Thank you. I'm back. So a few years ago, I went down to Boston for a week, and the American Association of Variable Star Observers was presenting a photometry course. So I went down to take the course, and while we were there, one of the things they did for the students was gave us a private tour of the Harvard College Observatory. And amongst several very interesting glass plates that they brought out, this is one that for me was a real excitement. This is Edwin Hubble's discovery image of the first extragalactic variable star. You can see what they were doing was they were shooting M31 with the 60-inch reflector and then the 100-inch reflector, looking for novae, and you can see that they were finding quite a lot of them, except that at one point he suddenly realized that this one up here was not a nova, it was in fact a variable star. And at that time, there was a big debate as to, is this actually a separate galaxy, or is this some sort of a swirly cloud of gas and dust within our galaxy? They actually had this idea that our galaxy was essentially the whole universe. That there was, they figured the size was about 300,000 light years, and then the rest of the billions of light years of universe was empty. If we switch it around upside down, you can see there's the star. There's a little faint arc of stars here, and then the wiggly line here. So I thought I would be able to maybe image this. So we zoom in a little closer. Doesn't really show a great deal more. So there's an image of the galaxy that I took with my 90 millimeter refractor a couple of years ago. And in January, that's the field of the Boltwood 40 centimeter scope with my ST2000 camera. And so that's a black and white picture from the telescope superimposed on the wide field view. We zoom in a little further, and well, let's go right in. So here's the view. You can see here's the wiggly line, here's the little arc of stars. So that right there is Hubble's variable. You can also see that there are some supergiant clusters. So any of the big bright stars in this view, of course, are in the foreground in our galaxy, but all the faint ones pretty much are actually in the Andromeda galaxy. So I thought it was pretty cool to be able to image a star in another galaxy. Now, this is a zoom in further, and if I flick back and forth on two different nights, you can see that the star is actually varying quite noticeably. Seeing, of course, varies from night to night as well, but but the star is clearly brighter in the second image than the first one. So, some years ago, there was some interest in this star, and so a lot of the old data was digitized, and now you can actually go to the AVSO and get the data. So this is Edwin Hubble's measurements. What I've done is I take it and I subtract multiple periods from the data so I can compress it all in so they all fit onto the cycle. So this is actually 2 cycles of a Cepheid variable star. Now, he discovered it in 1923, but of course he was able to go back and look at George Ritchie's images back as far as 1907, and then he observed it for another 4 or 5 years to get his curve. And then in the 50s, Walter Baade came along with the 200-inch telescope and collected another basically 2 falls from June through October or November in 1950, 1951. He collected data, and you can see that the data phases in nicely. The amplitudes are quite a bit larger. He was using different variables and different plates. I think Hubble may have been running into nonlinearity on the photographic plates. So then 9 years ago, somebody came up with, David Soderblom came up with the idea that the Hubble Space Telescope should take a picture of Hubble's first variable. And so they asked the observers of the AAVSO if they could observe the star for a few months so that they could be sure what the cycle was, because they don't want to waste Hubble Space Telescope time taking, like, if they're only going to take 2 or 3 images of it, they don't want to take them all at the same time. They don't want to take them all at the same magnitude spread over a few weeks. So they needed to know what was going on. So the HQA data, there's the green bow ties there, that's data collected by Arnie Hendon, who's a well-known advanced photometrist. He was the director of the AAVSO for many years. And of all the data they collected, his was the data I trusted the most. And so then I eventually was able to collect data on 6 different nights, and those are my measurements, the big purple circles. And you can see that with a period of 31.937 days, my data phases just beautifully with the data from almost 100 years ago. And it confirms that this star is continuing on its nice and regular beat, hasn't changed its period or anything. So, thank you.
Thank you, Rick. And last but not least, Paul Clonier.
Hi, sounds good. I'll try not to fumble it. Hi, everybody. Well, we've had a few good comets come in the last few months. In fact, the last few months have been actually rather nice for comets coming into the inner system and putting on a show. In December, Comet Virtanen became naked eye, did a nice dance near the Pleiades there, and under a dark sky you could see it with the naked eye. So this was a real banner one for this current state. So I photographed it back in December. I showed you some of those images. This is a month after that, so it's about almost 3 times as far away, but still shining quite nicely. No longer obviously a naked eye object, but still a nice photographic object, and you could definitely see it in the binoculars. So Virtanen put on a really nice show for us. Our nights to observe these, as many of you have noted, have been few and far between, so I had to take advantage of the nights that we did have. So on the same night I shot this, which was January the 12th, I shot this with a 300 millimeter lens and Canon 60DA. When I finished that run, I turned my 11-inch on another comet, and that's Stephanoterma. This little guy, not nearly as bright. Obviously, this is 10 times the focal length that I'm shooting at here. But again, not a lot of detail in the comet, but you can see there's definitely a bit of a curve to the tail. And unlike Virtanen, which didn't display much of a tail really, just more of that spherical halo, it definitely subtended a tail there, and you can see a fairly sharp edge especially on that side of the tail. And this is a result of our geometry, the way we're looking at it. So that was also the middle of January. Then we had a latecomer, a Johnny-come-lately, and that's Iwamoto. This was just discovered in late last year, and it's actually not a new comet coming into the system. We've determined that it is periodic, but it has an orbital period of something like 1,300 years. So the last time it was visible was in the 7th or 8th century. There are no recorded reports of this. No photographs either, no, unfortunately. But we did get a bit of a nice show on it. It's, as I say, a very long orbital period, and it won't be back into the inner system until almost the year 3400. So if you missed it, wait for it. So this I only shot 3 nights ago. We had a nice clear night, and let's see if I can. You can see it. This comet currently is trekking its way through the heart of Auriga. So we've got some really nice nebulosities in Auriga, a number of nice star clusters. Andrew showed M38 down there. So 3 nights ago, this comet was sailing through, and it's definitely moving in this direction. So again, if I didn't actually get a chance to see this with binoculars. I did try, but the night was a little bit dodgy. We've got some clear nights, a few clear nights coming up. So it's going to be in that general vicinity. If you've got a telescope or a good set of binoculars under dark sky, you might be able to check this out. But again, on this night, M36 and M38, beautiful clusters in Auriga. And obviously some nebulosity there as well. This was also shot with a 300 millimeter lens, piggybacking on my 11-inch. So comets, good stuff on the comets. I have one more thing to show you. Just good old Orion, everybody's favorite this time of the year. So the object that I've been trying to shoot this for a while, and it's challenging for a number of reasons. For one thing, it's very faint, this object I'm going to show you, and another thing is that it's sitting in a part of the sky that just like every GeoSat satellite rips through that field. I mean, all the subs that I shot of this, I usually get at least 1 or 2 satellites ripping through there. I think, Oscar, you can attest to that. You've had some challenges with that too. This is a very large object, and what I've done here, it's the Witchhead Nebula. And if you were paying attention, which I'm sure you were all, to Terrace's lovely deep image of Orion, you'll notice I don't think there was much there. Your image went really deep on the hydrogen alpha, Barnard's loop and stuff, but the Witchhead is extremely faint. You can see here it's actually kind of nipping on Orion's foot there. So I'll subtract Orion there. So what I've done is I've taken a high resolution image and I've superimposed it on this and brightened it up substantially, because if you're just taking an image of the sky at that particular depth, there's no way you're going to see that object. So, but it's an interesting object because star Rigel down here is what's causing it to light up. Rigel is a very hot blue star, throws out a lot of UV, throws out a lot of intense blue light, and that whole area is rich in dust and gas. There's a lot of, well, as you saw in Terrace's image, there's a lot of gas and dust floating around in the entire Orion region. But this is an interesting nebula because relatively close to Rigel, this whole complex is about 700 to 800 light years away. And Rigel is basically illuminating this denser collection of dust, and that dust is very efficient at scattering blue light, just like the oxygen and the nitrogen in our atmosphere is efficient at scattering blue from sunlight and giving us blue skies. Here it's dust in the nebula reflecting the light from Rigel. So the whole nebula, by the way, is about 70 light years across. It's a fairly large structure, but again, it's very faint. So this is the close-up I took of it. And that's the Witchhead. Now, I prefer upside down because I think she lives up to her name more when she's upside down. So in this view, Rigel is just off the screen up here. I purposely took it out there so I wouldn't get a a super crazy gradient there. But you can see there's dust floating around through here and a lot of gas and that. This star is not the one that's lighting up Rigel. Rigel up here and lighting up the nebula here. So this is a 70-minute exposure, again with a 300 millimeter lens and a Canon 60DA. I was going to save this to Halloween, but I thought, well, what the heck. Thank you very much.
Yeah, thanks, Paul. I've definitely taken a crack at this object myself, and all my sub-exposures are littered with geostationary sats just flying through the field. So I've got to work on it. All right, moving right along, we're going to hop into the observing challenge. So last month, the beginner challenge was M1, the intermediate challenge was Caldwell 49, advanced challenge was Sharpless 2-301, and the lunar challenge, of which we saw a few submissions, was the Alpine Valley Rail. This month, we're going to start off with M78 as the beginner challenge. It's just off the hip of Orion there. It's an emission nebula, about eighth magnitude in brightness, 8 arc minutes in size, and it's about 2.5 degrees, that's supposed to say northeast of Altenac, but I put this slide together late. I must have been tired. For the intermediate challenge, we'll do IC418, which is a tiny little planetary nebula in Lepus, approximately 9.3 in magnitude. It's rather bright, pretty tiny at about 12 arc seconds in apparent size, so that'll be a fairly challenging object to nav. You'll probably need a rather large instrument. For our advanced challenge, we'll take ARP82, which is a pair of interacting galaxies in the constellation Cancer. The galaxies are individually cataloged as NGC 2535 and 2536, and they are 13.3rd and 14.7th magnitude in brightness. For some reason, I didn't say which constellation they're in, but Serpens, I think. Oh, no, Cancer, yes, it's right there. Must be tired still. All right, moving right along. The lunar challenge, we'll do the Bailey crater. So it's a huge impact scar on the southwest limb of the moon. It's about 303 kilometers in diameter, which is over 9% the diameter of the moon, so it's quite a huge thing. Visually, though, it's not so large because it's on the limb, so you're getting a really kind of oblate view of it. So it's this little, this area right there. So it is classified as a walled plane, and it's best observed on days 13 and 23 to 24, lunar days 13 and 23 to 24. All right, so just to recap, the beginner challenge will be Messier 78, the intermediate challenge IC418, the advanced challenge ARP82, and the lunar challenge Bailey Crater. So I hope to see some submissions of these objects next month, and we'll try to remember to send these out to the mailing list, but if I forget, someone poke me. All right, and up next I'm going to welcome Sharon Odell to the podium to give us an update on the Dominion Observatory. Sharon?
So in regard to the Dominion Observatory, the RASC Ottawa Centre has agreed to act as a sponsoring organization, and a subcommittee has been formed consisting of Douglas O'Brien, Mike Mockham, Tim Cole, and myself, as agreed upon at the last council meeting held on the 21st of February. Other members may join in future if they are interested in assisting. At the moment, the History Committee of the RASC National Office has also expressed an interest to support us, as they may have advice based on their experience taking from protecting the David Dunlap Observatory in Toronto. Why we are motivated to protect the Dominion Observatory is centered on protecting the architecture as an example of historic Canadian scientific architecture. Whereas of present, it is only has an honorary mention of heritage for being constructed by the Dominion architect David Ewart and for its Romanesque revival style. Stephen J. Dick mentions in his 1991 list of national observatories an overview of some of the most important observatories in the world. And the Dominion Observatory of Ottawa, built in 1903, makes that criteria, along with its sister observatory, the Dominion Astrophysical, one built in 1918 in BC. The delegates meeting that's seen in this photo from 1911 shows the Astronomical and Astrophysical Society of America, meeting at the Dominion Observatory in Ottawa at the entranceway, seen here behind them. This is when they actually made the decision to build the Dominion Astrophysical Observatory. The reason why we are seeking a scientific heritage designation for the Dominion Observatory buildings as a whole is also in hope of maintaining the important history of the astronomers and scientists who also worked in this observatory, both women and men, at a national reporting level of astronomy. As seen in these two correspondences that were written within the Dominion Observatory during the year of 1946, the content explains how important it was to continue education on what Canadians were pursuing in astronomy, to have an understanding of what the observatory was doing at that present time, and for imparting information that may motivate youth to enter physics and astronomy for themselves. This is an objective our subcommittee would like to continue through preserving the scientific architecture of the Dominion Observatory for the present time and into the lengthy future. RASC Ottawa used to have its meetings at the Dominion Observatory location, seen in this 1948 pamphlet, where once members would set up their own telescopes in addition to the observatory ones, bringing us to another motivator to request protection for this majestic building, for its heritage, and to prevent future construction of the Ottawa Hospital from encroaching on the environs which make up the observatory campus and grounds. This is a recap of what I showed last year of the site where the observatory is. If you look in the top corner where Maple Drive is, that's where the observatory building is. It's very faint. Where the pointer is, if people can see it. It's on the clicker. So it's right here. That's the dome roof. That's seismology. That's the campus area. And this is how close the hospital grounds are here, right in the front lawn, or where they will be. This is what the hospital will look like. Right now it's about between 12 and 20 stories high. They haven't completely decided yet. This green roof lot vents, these are vents. This is where the parking lot is supposed to be underground, but the original plan was to have above parking because it would cost less. That might return to that plan because as the building and things are getting settled with building the building and the plans, et cetera, there might be a shortage of funds to continue, and so this is another reason why we have to protect the area around the Dominion Observatory environs. So the Dominion Observatory is here in this corner, so this will be blocking the side of view of the observatory. And if this is all raised parking structure, then the front, basically it'll be blanked out. Here's another shot, closer. There's the observatory up here. This is the front yard. This is where the building is supposed to back onto for the new hospital, and this is all the parking that's supposed to be in this area here. The Transepts telescope that you see in this image, and many of you may already know, of the Ottawa Citizen article that was written and published this past late January by Michael Wolfson. Mr. Wolfson pointed out how the telescopes associated with this main observatory and the other buildings around it, such as the transept one here, played a critical role for Canada and the astronomy. Sir Sanford Fleming is mentioned on a plaque at the front of the observatory, and Canada's role with time. The prime meridian, or the Canadian prime meridian, basically referencing back to Greenwich in Britain, is something that Douglas O'Brien has made up or has mentioned many times as well as being critically important to developing the country and boundaries. This article here is from Parks Canada, and it's just an example. This one is based on Building 7. So each of the buildings on the observatory campus got numbers. And the main observatory building is number 1, and then it subsequently goes through all the numbers around the area. And so seismology here, this example written up by Parks Canada basically indicates the character being that of the Edwardian classical style near the end of the paragraph near the bottom. And it's just an honorary heritage designation. It's not a real legal designation. There's what the number 7 symbol looks like, and on the observatory building itself, it's at the front entrance. Now I'm bringing you to the Canadian Science Museum that I went to visit this past February. Oh, and I guess it's break time.
Were you expecting another slide?
Yeah, I was expecting a whole group of slides. They went missing.
I guess they went missing. I don't know. Okay.
Do you want to find them after the break?
Yeah, we'll dig for them after the break. The video that you sent us is in the break, so I don't know if you want to speak to that video. We'll show it during the break.
Sure. So the slides that are missing are images of one of the telescopes from the observatory that's now on display. The refractor telescope was taken down when they closed the observatory that was outside in the front yard, and the Helen Sawyer Hogg one. And so I was just going to show what telescope is up on display in any reference to the Dominion Observatory today, and leading into the fact that they also have a display on Indigenous astronomy now, and also the exhibits that are in the Ottawa area on women astronomers. So the video during the break is a little cameo on Victoria Caspi, who works at McGill University, and Oscar will play that during the break.
Just a few questions, Sharon.
Mm-hmm.
First question, the possibility of a tour of the observatory?
The observatory now houses the Office of Energy Efficiency, so it's government staff, and they are not allowing tours at this moment. Yeah.
Not at all, or?
No, not at all, because there's a lot of important work, I guess, that they want to. It's a high security area, because there's also seismology working there, and the buildings that are around the seismology building and everything, they have to keep a high security for the work that they're doing there.
The other question I have, that telescope that they have at the Science Museum, what's the chance of bringing that back to the observatory?
I have no idea at this moment, but I do know that we're trying to protect the building itself, which definitely refers to that telescope.
Right. It'd be nice to be able to see the observatory.
Yes, it would, yep.
Okay.
You're welcome.
Too much politics.
Sorry about that. All right, so we'll go to break. I'll play the video that Sharon sent us during the break. It's 8:35 right now. Let's take 10 minutes and get back here at 8:45. All right. So Chris went digging during the break, and he was able to find the rest of Sharon's slides. So I apologize, Sharon, for that technical difficulty there, but we found them, and I'll let you take it away again.
Okay, we're back. So at the Canadian Science and Technology Museum a couple weeks ago, this is what the display looks like. I apologize for all the kickback of light when I was taking photos, but this is the telescope that they promised they would put up on display when the museum reopened again after its renos in 2018. And it does have reference to the Dominion Observatory and where the lenses, etc., were made by John A. Brashear. This is what it looks like on display. So this is what they've put in instead of the refractor that we used to know being there. So it's the double astrograph from 1912. Here's some details of what it looks like from different angles, so you can really get a look at it. The mechanisms inside the little window, the little door. It's kind of neat to look at. This is where it used to come from. This is just a side angle, left side yard view of the observatory grounds and the campus, and the small observatory at the other left side there is where it used to be housed. This is just the other objects that are, and displays that are right next door to the telescope. And I'm just showing how a lot of kids, I saw kid after kid after kid going up to try and look into the telescope that they have there for children. And then, of course, the many astronomies with indigenous display, trying to look into those histories as well. They had a cool Science Saturday the following weekend, and apparently they just started this last year. It's new. And the reason why I brought this up is because Natural Resources was there from the Geological Survey, and that's the image, I believe, to your left. And they had a fake volcano, what seismology does, and basically some of the activities that the observatory used to have in it years ago. There was another setup with the geologist looking at rock and bones, etc. And then over to the far right is an image of University of Waterloo using liquid nitrogen and showing how magnets work and that they can float around on that disk. The reason why I brought up Waterloo is that this past December, you might have noticed in the news, we had the first Canadian woman to win the Nobel Prize in physics. And the last time a woman won a prize in physics was Maria Goeppert-Mayer in 1963, and before that was Marie Curie in 1903. So she's one of three ever to have won it. And of course, the last time in 1963 was 55 years ago. There is another exhibit on, which I decided to take a photo of the Courage and Passion exhibition. Basically, it's focusing on Canadian women in the natural sciences. I took an image of the building outside because the same Dominion architect also built the Victoria Memorial Museum downtown off of McLeod. This is what the exhibit looks like, and it basically is trying to encourage girls and women into science and especially into physics. This professor here, Victoria Caspi, she works in physics at the McGill University, and that was a video that played at break, and it is available at the museum as well. She is an astrophysicist who studies neutron stars, and she's the first woman and the youngest person to receive the Hertzberg Medal, Canada's top award for science and engineering, with the prize of $1 million. The Courage and Passion exhibition is on until the 31st of March, and I encourage you to go see it. It's free entry on Thursday evenings after 4:30, 5 o'clock, and it definitely is a must-see. And it brings us back to Dominion Observatory again. Mary Gray, of course, from my presentation back in 2017, was a woman astronomer at the Dominion Observatory, the last one to work there, and basically pioneering. Again, another view of the Dominion Observatory, and a recap of why it's important to preserve this scientific building. Thank you.
Thank you, Sharon. I'm glad we were able to find the rest of the slides for you there. All right. Oop. All right, so up next, I'm excited to have our next guest. Back in September, I had the good fortune to be listening to CBC's science talk show, Quirks and Quarks, where I happened to catch a segment featuring Dr. Kaplan. And I thought to myself, I have to bring him to present to the group. I fired off an email, and fortunately we were able to coordinate a visit. Dr. Kaplan is a Canadian Institute for Theoretical Astrophysics National Fellow at McGill University, where he studies astromaterials and neutron star crusts. He received his BSc in physics from the University of Virginia in 2013 and his PhD from Indiana University in 2017, with a dissertation on the theory of neutron star crusts. Beyond academia, Dr. Kaplan works as a science writer for PBS Digital Studios and the Kursagat Design Studio, having written extensively on topics such as space elevators, wormholes, and alien megastructures. So it's my pleasure to invite Dr. Kaplan up to the podium tonight. Dr. Kaplan.
Thanks so much, and I really appreciate the chance to be here. One thing I do want to say is, since I am at McGill working on neutron stars, I know Vicky Caspi personally, the woman highlighted in the slides just before I came up here. And I will have to second the recommendation that you all go check that out. She's a fantastic scientist, and she does very interesting research. And I haven't seen that piece of media myself that was being advertised, but it has to be fantastic, just knowing her and what she does. So I'm going to tell you a little bit about my research on neutron stars. And I'm actually a physicist, not an astronomer, so many of you are probably better astronomers than me. So this is going to be a talk about everything below the surface of the star, and we're going to dive into the inner lives of these dead stars. Oh, isn't that great? There's my title slide. What fuses the elements heavier than iron? Or put another way, where does gold come from? You probably think that you know the answer to this question. And I'm going to come back to this at the end of my talk. But just keep in mind that things come from somewhere. And so all of the gold in your wedding rings, all of the uranium in the nuclear reactors around here that might be powering the lights, they come from somewhere. And I just want you to hold that question in your mind for the next half hour. Where do they come from? Because 13 billion years ago, this was the pie chart making up the composition of the universe. It's about 75% hydrogen, 25% helium, and then there's trace other that really isn't even worth mentioning here. I'm not really sure where this yellow came from. That might be an error in my slides. Maybe this is the dark matter, so it's invisible and you can't see the yellow. And today, 13 billion years later, the pie chart still pretty much looks the same. There's this very tiny sliver of trace, which is everything from kind of lithium all the way up the periodic table. And that is where all the interesting chemistry happens, and everything in this room that really makes this whole event possible comes from. So something important happened to that 1% of the universe, and I'm going to take you there tonight. Okay, here's the hero of our story. What is this? You're right, it is a proton. Thank you. This is the hero of our story. This is a proton 13 billion years ago sitting around after the Big Bang going, oh geez, I exist. What do I do now? He's the hero of our story. We're going to follow him. At some point, all of this science happened. So there were stars that formed, gravity pulled hydrogen and helium together, and hydrogen started to burn. It could fuse. And so it fused and it made helium, and that helium fused to make bigger helium. And then when that star ran out of helium or hydrogen to burn, it burned helium in this thing called the triple alpha process. It made carbon. That catalyzed this thing called the CNO cycle. And all of these burning processes were happening in the cores of stars. And so there was this radiation and heat that's pushing outwards, propping stars up while gravity squeezes it in. It's a giant pressure cooker for nuclear physics that's making the lightest elements in the universe. Stars adopt this onion shape. I think you probably all know this. You have a passing interest in astronomy if you're here. They get this onion shape where the hydrogen burns into helium, which makes a helium core, which can then ignite and make carbon. And you can make progressively heavier things up the periodic table until you get to iron. Stars develop, the biggest stars develop these inert cores of iron, which can't actually fuse. And I'm a nuclear physicist, so the reason comes from nuclear physics. It's the binding energy. It's how much energy is left in that proton to be squeezed out by fusion. Turns out you release a lot of energy. This is energy release when you fuse, and this is energy release when you undergo fission, when you split a nucleus. So at some point, you can't just fuse all the way up and then fission all the way down. You can't do that forever because conservation of energy. So you get stuck. And the place where you get stuck, where the ball is sort of at the bottom of the hill, is iron. So iron is nuclear ash. Iron can't be burned. You can't squeeze anything else out of iron. So you're kind of stuck once you get to 26 protons in the nucleus. So this is what the core of a star looks like. Here's a bunch of iron nuclei. Here's a bunch of electrons around them. And without fusion, without the heat being provided to prop up the core of the star, it will eventually implode. So there is pressure that's provided by these electrons, which is overcome, and they are in a way squeezed into the protons. And that makes a very large number of neutrons, and only a few protons survive. And then these things called neutrinos, these very ghostly cousins of electrons, which then come streaming out of the core of the star. Without those electrons in between, it all just kind of clumps together. So this was 5 nuclei, but the core of the star has 10 to the 55 or so nuclei. I'm sorry, I'm getting like a echo. Should I stand back?
Yeah, I think your batteries are dead and your wireless. Keep the wireless off.
Okay, I'll just stick with the podium then. So this is 5 nuclei, and really it's happening over the course of like 10 to the 50 nuclei. So this is a lot of nuclear matter that is now just being smushed together to make one giant nucleus in space. So a star, its core implodes, neutrinos come streaming out, and they push off those outer layers of the star, and you get an explosion. That's the basic principle and mechanism driving these things that we call supernova. Since this is an astronomy meeting, I have to put up these pictures because they're just too pretty not to look at. This is the crab. This exploded about 1,000 years ago. It was observed by Chinese astronomers, and there might be some rock carvings in New Mexico that indicate that it was observed there as well. And they're the most, or among the most luminous electromagnetic events in the universe. This is a galaxy. This is a supernova. They can really outshine entire galaxies for weeks at a time before eventually they fade from view and turn into one of these nice remnants. Okay, so I like neutron stars because I'm a theoretical physicist. This is what I work on. So I'm going to sort of dive into that remnant, that thing that's left at the core of the supernova, for the next chunk of my talk. So I'm going to do just a tiny bit of math, just an ever so tiny bit of math, just doing order of magnitude estimates. So the size of an atom, this is an angstrom, 10 to the minus 10 meters. A nucleus is 10,000 times smaller than that. So just based on these scales, a factor of 10,000 or 100,000 difference, excuse me, if your head was a nucleus, how far away would the next person have to stand to make a scale model of sort of the atoms that make up you and me? Who said it? About 50,000 feet, that's right. So what is that, like 5 to 10 miles or so? Yeah. So you have to go like well into Gatineau to find like the next person. That's how spread out everybody in this room would have to be if you were atoms on Earth. But if you are atoms in a neutron star, you will all be packed into this room. So that's the difference in density between a neutron star and typical matter that you're used to, like in this room. Okay, so here is Ottawa and sort of the surrounding area. Yeah, so you got to go about 5 miles. So neutron stars are so dense that Mount Everest would fit in like a cup of coffee. It wouldn't be much bigger than like the microphone right here. You could take every human being that's alive today and you could squeeze them down to the size of like a piece of candy. It's absolutely remarkable how compact and how dense these objects are. They're the densest thing this side of a black hole's event horizon. So if you take the mass of the sun, like you might in, say, a supernova, and you take all of that matter and you squeeze it down to just the nuclear matter that's left, and you dropped a solar mass neutron star on Ottawa, it doesn't really even reach Gatineau Park. Like maybe just the little entrance right there. They are incredibly compact. They are incredibly dense. And this makes them awesome laboratories for physics. Okay, I should warn you, this is my last slide with mathy things. It's not going to go above the stuff you saw in high school, and I'm going to put it all in context, so don't be scared. Okay, a factor of 100,000 change in radius, right? I'm going to change by 10 to the minus 5. So how does the neutron star behave relative to what it was before? Conservation of angular momentum. Spinning is conserved. There is a fixed amount of spinning sort of in the universe. So if the star was rotating, it will continue to rotate, but now as a very tiny compact object. So since this scales like radius squared, this is a factor of 10 billion change in rotational period. The sun, it takes what, 25 days to rotate? Is that right? Solar observers? 23? Okay. So if you take that and you speed it up by like 10 billion times, you get something that's in the neighborhood of a few milliseconds. So these are things that are the mass of the sun, that are the size of the city, that are spinning 10, 20, 30 times a second. It's kind of the mechanism for pulsars. That's what's being shown right here. Okay, the escape velocity. How fast do you need to throw something straight up in order for it to be fast enough to never come back down again? That's the escape velocity. Well, just plug in some numbers and you get the escape velocity is 0.5 c, the speed of light. So don't drop your keys on a neutron star because you will not be getting them back. And also, going the other direction, throwing up something, you have to throw it at half the speed of light to get it off. That means that if you drop something, it hits at about half the speed of light. So that can power some really wicked emissions of X-rays from neutron stars that are accreting, that are actually pulling matter onto them. They can be very, very bright despite the fact that they're so small. And then the last thing, this one's kind of weird, so I won't waste too much time with it. There's this thing called magnetic flux. So you can sort of count up the magnetic field lines, and then if you just sort of bundle all of the magnetic field lines together through a much smaller object, you get that there's, again, a 10 billion factor increase in magnetic field. So the magnetic field of a typical star is 10 to the 3 Gauss, are the units that we like to use, 100th of a Tesla. So it goes up to about 10 to the 13, maybe even 10 to the 15 Gauss. Does anybody have a sense for how big this is? Because I actually don't. I'm a theoretical physicist, and I literally don't have a sense of scale for this because there is nothing for comparison. It is the strongest magnetic field in the universe, period. It's the strongest magnetic fields we know of are around newly born neutron stars, which we call magnetars. So these are incredible laboratories for fundamental physics, just based on some of their simple physical properties.
How can it have a magnetic field if it's not
So
charged?
that's a great question. It doesn't necessarily have to be charged. It just needs to have, it just needs to be magnetized. And it contains, if you remember my slide a few ago, it had just a few protons and just a few electrons left. It's the protons and electrons left over in the neutron star that make up about 1% of the star that support the magnetic fields. And they're the only objects in the universe where all 4 of the fundamental forces actually play important roles. To understand what's happening in this room, you need electromagnetism because that's sort of how atoms and electrons bond, and maybe gravity so that we don't float out of our seats. But you don't really care about the nuclear forces. And anywhere you go in the universe, you only really need 1 or 2 of these forces to understand what's happening. A neutron star, if you're a neutron star theorist like me, you need to consider general relativity, electromagnetism, and the 2 nuclear forces in order to really comprehend what's going on. So these are, again, phenomenal laboratories for physics. And to give you one more point to emphasize how great they are, this is sort of a size of known nuclei on a log scale. So if there's 1, that's a proton. Of order 10, that's between carbon and magnesium. 10 to the 2, that's about 100. That's silver. Uranium is 200 some protons and neutrons. A neutron star is 10 to the 57. So I'm not just doing this for the haha, big numbers, aren't they fun? Imagine you're a social scientist. I mean, forget physics for a second. Imagine you're a social scientist, and you say, I want to study how groups of people interact. And I'm going to study a husband and wife. I'm going to study 2 people, how these 2 people have a relationship. I'm going to study a little paper company office in Scranton, Pennsylvania, 10 people, how 10 people interact. And then I'm going to study global politics of 7 billion people. And those are your data points. And that's kind of what we are as nuclear physicists. We have these data points of really small numbers of how protons and neutrons interact from the atoms that exist on Earth. And then we have neutron stars all the way on the far end of the scale. So they are these great, great data points for extrapolating models and testing theory in a way that we just can't access on Earth. But who cares, says the straw man, who I will now happily knock down. Why does this matter? For one thing, they tell a story about the history of the universe, right? I mean, there were supernova, and there were all of these things that happened in stars that made them. So there's information about the history of the universe and how the universe got to look like it does today in neutron stars. And they literally, being the densest objects in the universe, they contain matter that hasn't existed since the beginning of the universe. The cores of neutron stars contain matter in the state that it was in prior to the first microsecond after the Big Bang. So they are fossils. And that's really remarkable. They can let us probe the earliest moments of the universe. And lastly, they're a part of the universe and what it's doing now. So let's dive in. I'm going to go into a neutron star really quick. I've told you again and again that they're like a giant nucleus in space of protons and neutrons smushed together. But in many ways, they're like the Earth. They have a liquid core of nuclear matter, but then they have this crust. So think about the Earth for a second. If you go up to where the International Space Station is, you almost feel nothing. It's a vacuum. There's a few atoms here and there, and it's very low density, very low pressure. But then jump out of the International Space Station and start to free fall. Do a Felix Baumgartner dive through the atmosphere. The pressure is going to go up, the density is going to go up, and there's going to be more and more atoms around you, and the temperature is going to increase until you hit this thing called the ground. On neutron stars, despite the fact that their surface temperature is 500,000 Kelvin, the pressure from gravity is so high that nuclei are actually forced together into a lattice. They actually do form a crystalline solid over the outermost kilometer-ish of the star. So they have this solid layer above this liquid core. And that core can contain God knows what, quark gluon plasma maybe. And then there's sort of 14 orders of magnitude in density increase from vacuum to being sort of that Mount Everest in a cup of coffee. So let's walk through it. Let's drop an iron nucleus onto the crust and send it to very high density and depth. So you're about 100 meters down, and you're about 100 times the density of the core of the sun already. And this is going to be an iron nucleus, and he's going to have all his little electron friends around him. So this is sort of near the top of the star. As you go down, as you drop through the crust, that electron energy is going to increase, the same as it did prior to the supernova. All of that squeezing makes the electrons have a much higher energy. And eventually, the electrons won't want to stay out of the protons anymore. It becomes energetically favorable to eat them and turn them into neutrons in order to get rid of some of that electron energy. So you make neutrons. And I think you can see where this is going and how they get the name neutron star. You keep going down, and you keep capturing more and more of these electrons, and that nucleus becomes more and more neutron-rich until eventually there's so many neutrons in the nucleus that it can't actually hold them together anymore, and they just start to fall off. And so you get this gas of neutrons that sort of is also, along with that electron gas, around this very, very neutron-rich nucleus. And you can keep going down in depth, and the same thing keeps happening. You capture more electrons, and you make more neutrons. And it keeps happening, and it keeps happening until the density is so high that neighboring nuclei actually will fuse together. They'll just spontaneously fuse. The quantum mechanical tunneling and all sorts of magic will make them fuse. And this is actually cold fusion. So this is just probability-based spontaneous fusion based on density alone. So it's cold fusion by any other name. And they'll fuse, and then undergo all those nuclear reactions again to make more neutrons. And it keeps happening. That'll happen again, and it'll happen again until those nuclei are so close that they touch. And this is about 1 kilometer down, densities of 10 to the 13 grams per cubic centimeter. I mean, it's just the densest thing where everything except for a few gaps in between nuclei are filled with protons and neutrons. And the nuclei start to get very fuzzy. The bounds of whether or not a neutron is attached to any given nucleus gets very fuzzy. And when this happens, there's a phase transition. And I do literally mean a phase transition, like liquid turning into solid when it freezes, or sort of vaporizing into gas. There's literally a phase transition, only now it's happening at the level of individual protons and neutrons. And they get squeezed together, and they form weird shapes. So there's nuclei up here. Sort of the top of the crust is actually made of nuclei just like you and me, but the core is this bath of protons and neutrons all smushed together. So there's a nuclear phase transition in between where nuclei start to touch and they rearrange. We call them pasta because they look like spaghetti and lasagna. if you imagine taking a whole bunch of marbles and lining them up in a row, you could imagine how they might look like a strand of spaghetti if you had a whole bunch of balls all in a row. Or if you spilled out a whole bunch of spaghetti and you took a whole bunch of strands of spaghetti and then just sort of smushed them together to make a sheet, you could imagine making something that looks sort of like lasagna. So those are the phase transitions that occur in the crust as they actually become these sheets with millions of protons and neutrons in structures together. Big boring slide here about the history of this, but some papers in the 1980s thought about this and they came up with these spaghettis and these lasagnas. And it's just because there's two forces. Protons repel. There's still some protons. Protons push each other away, but protons and neutrons pull each other together really, really tightly. And so they compete. These forces compete, and they make these funny shapes. This is one of my favorite slides. On the left are some simulations that I did for my PhD, and on the right are some of those theoretical sketches from the 1980s. It is remarkable agreement between theory and more theory. So you start with nuclei. I like to call them gnocchi at this point. Squeeze them together, you make spaghetti. Squeeze them together, you make lasagna. Squeeze them together, you make anti-spaghetti, and squeeze them together a little more, and you make anti-gnocchi. Some people call this Swiss cheese. Those people are wrong. It is anti-gnocchi. And I have a video. So this is what it might look like if you were to blow some of this stuff up. So if you started at the bottom of the crust and worked your way up. So you're seeing some of those Swiss cheesy anti-spaghetti phases right now. And this simulation is sort of expanding and blowing up a bit. You now have lasagna, and the density is decreasing, and you're imagining going up in the crust. And these sheets will eventually fission themselves and form those spaghetti things. And I'll also draw your attention to the scale. This is all happening at a nuclear scale of femtometers. There's these sort of thermal fluctuations that you're seeing as they wiggle along. They also have a nice hexagonal packing. That's pretty cool that even the spaghetti makes a nice sort of crystal in a way. And eventually the spaghetti all falls apart and you get nuclei again, right around now-ish. And you can even see the crystal planes edge on there for a second, so it does form a nice crystal. And that's it. You know, this was basically my PhD thesis in 10 seconds, was doing some of these simulations. Something else this is a figure from a paper that Andre Schneider wrote. He was also in my group, did his PhD just before me. If you tune some of the knobs, some of these plates, the holes will appear in them. And so these are sort of plates, but with this sort of hexagonal lattice of holes. We called them waffles because why not? When you're the first to observe something in science, you get naming rights. They're the most expensive things in science, and we have them. And this is what we burn them on. This paper's title is literally Nuclear Waffles. Very proud of that fact. Okay, so why does the crust matter? Why should you care? Why should you be interested in anything I'm telling you? This is just theory. Well, the crust is the outer layer, right? The crust is the part of the star that you see. So if you want to observe a neutron star and interpret something about its core that has all of that rich physics, and if you want to understand the fundamental physics tests that are held there in the neutron star, you have to understand the crust. Because if you don't understand the crust, you don't understand anything. So I say that exact sentence at talks all over the world all the time because it gives me a job, essentially. Because I'm a theorist who works on crusts. And I'll just say that this is maybe a boring slide for this audience, but is kind of my life's work. So the physical properties of materials affect how they look and how they behave. So the thermal conductivity and the heat capacity tells you how heat can dissipate and move through crusts, and that affects how crusts can cool off after a supernova, how they can cool off in these accreting X-ray systems. And likewise, the electrical conductivity, how electrons move through the crust, tells you how the magnetic field can evolve, how magnetars lose their magnetic fields as the neutron star ages. If there is a crust, there can be mountains. You can make lumps on it. So just like on the Earth, we have the Himalayas and we have crustal dynamics. Crustal dynamics may be making gravitational waves. There may be starquakes, analogous to earthquakes, happening in the crust. Neutrinos, that's a big hot button topic amongst theory right now, is observing and detecting neutrinos from any source we can. And also nucleosynthesis. Matter can be ejected. I know I told you that you have to go half the speed of light to get something out. And you actually can, under certain circumstances, get things out of a neutron star. And that can make some of those heavy elements that I mentioned at the very start of my talk. So there are these things called gravitational waves. LIGO, the Laser Interferometer Gravitational Wave Observatory, has observed about 10 black hole mergers and 2 neutron stars merge at this point over the past 5 years or so. Maybe they'll detect gravitational waves from mountains on neutron stars in the future. It's possible. I've written a paper on it. I'm very optimistic, but I won't bore you anymore with that. But LIGO can detect these objects merging 1 billion light years away just based on the ripples that they make in space-time. On August 17th, 2017, 2 neutron stars merged. This is LIGO, the observer, who is celebrating her observation of these 2 neutron stars negotiating their merger. And this was a very big thing that happened in the science news maybe about 2 years ago now. Which is that we saw this thing, this neutron star merger and this kilonova and these gravitational waves, and it was the most well-characterized event in astronomy history. Basically, every observatory on the planet and every astronomer was staring at this thing for months to get as much data as they could to really understand the physics of it. And it's really important because, like I said, tests of fundamental physics and understanding why our universe looks the way it does today. So how do you make neutron stars merge? Well, you start with two regular stars. You make them supernova, one before the other generally, not both at the same time. And then you just have them orbit each other for like 1 billion years, going around and around and around, and their orbit decays ever so slowly as they radiate gravitational waves, right until the end when they slam into each other. So they spiral in, they go around each other, they spiral in. This is the gravitational wave amplitude. And then they get very loud. There's this chirp where they go whoop, and they slam into each other, and that ejects matter. So now there's this disk of matter that's coming off of the neutron star. Here's a great video of it as well. And I just want to emphasize that they make so many cool things. They make gravitational waves, but they also make these things called gamma ray bursts, and they eject this neutron-rich matter. There's this thing that we have now settled on calling a kilonova, which is sort of the explosion as matter sort of gets thrown out. Give it a few more milliseconds of simulation time, and you'll see the matter getting thrown out of the 2 neutron stars. There you go. This is the start of the kilonova. It's like a supernova, but nowhere near as bright. And then eventually, all of this stuff in the middle is at such high density that it has no choice but to collapse to a black hole. These are very, very awesome events. And is it going to collapse, or did I pick the wrong movie? Time will tell. There it goes, and it collapses to a black hole. So let's follow some of that matter that was in the crust. Let me show you again. This is what it looks like inside that neutron star crust. This is what pasta might look like. Lots and lots of neutrons, a few embedded protons and electrons, which support the magnetic field, whoever asked that question. Protons, neutrons, and electrons. And it's ejected and it decompresses, just like in that video I showed of matter sort of blowing up and falling apart. So the matter is going to fragment, and it's going to form seeds, which are very, very neutron-rich. 1 or 2 protons can hold on to 10 to 20 neutrons. They'll make nuclei that just don't exist on Earth because they'd fall apart in our environment without all of these sort of neutrons around them. It's sort of like a vapor pressure. And those neutrons are going to capture, and they're going to decay. They're going to do the opposite of the thing that happened in the supernova, and that's going to make electrons. And they're going to do this over and over again. They'll fission, and they'll keep capturing until they sort of run out of neutrons to capture. And they just do this. You know, this takes milliseconds, but it makes very, very, very heavy neutron-rich nuclei. So at the start of my talk, I started with a question that says, what fuses the elements heavier than iron? And then I immediately told you, well, you can't fuse things heavier than iron because fusion is this burning process, and you can't burn ash. So it's actually this trick of ejecting neutron-rich matter from neutron stars and neutron star mergers that seems to make the heaviest elements in the universe. It seems to be the place that gold and uranium and all these other heavy elements come from. So that's really remarkable that our understanding of the universe has changed so much just in the past 2 years of, you know, why the universe looks the way it does today. It's actually neutron star mergers now, so as far as we can tell. This is a great slide, which just shows sort of relative contributions of different celestial phenomena and sources to the periodic table. Obviously, the Big Bang, like I said, hydrogen and helium, and there's a very trace amount of helium that's now been produced by stars since then, burning hydrogen. And then everything kind of getting up to iron, and even a little bit past it is exploding massive stars. Supernova do make some of these light elements. But then to really, really get up there and really push all the way up to uranium, you do need merging neutron stars. So I'd just like to gush for a second, since this is kind of my life's work so far, is just studying neutron stars. They just have this awesome richness in structure and physics. They're more than a giant nucleus in space. It's more than a giant nucleus in space, excuse me. They have a crust, they have a magnetic field, they may have mountains, and there's still so much more to be discovered from them. And they're these laboratories where we can test fundamental physics, maybe not today, but maybe sometime in the near future. And I think Carl Sagan may have said it first, the stars died so you could be here. And I'd like to amend that because we now know slightly better. They didn't just die once. They had to die over and over and over again. They had to supernova. And then those neutron stars had to merge and form a black hole. So at least the star had to die twice in order to make the things so that we could be here. And I think that's a really awesome note to end on, is that even when they're dead, they still have so much to give. So that is all I wanted to tell you about tonight. And I think more importantly, there should be a chance to ask questions. So I will stop talking, and I will now let you start talking. So thank you very much for your attention.
Yeah, so we'll take some questions. Jim?
How do we detect neutron stars?
That depends on what flavor of neutron star it might be. Yes, the question was, how do we detect neutron stars? And the answer is that it depends on the flavor of the neutron star. So some of them we detect only in gravitational waves, like that merger. Others are pulsars. They are spinning 10 times a second, and they have a radio beacon coming off of their magnetic pole. So every time they spin and they sweep around, they go bam, and they blast us with this radio radiation. And those are pulsars. And that's how neutron stars were first observed, is in the radio. If you go up above the atmosphere and you put on X-ray goggles and you look out at the galactic disk, you will see bonfires. There are bright, bright sources in the galactic plane, which are neutron stars that are pulling matter off of another star onto them. And since it's hitting them at half the speed of light, it makes these bright, bright X-ray sources. Can't see them on the ground because the atmosphere blocks it, but if you go up to Chandra, you can see these X-ray sources. So it all depends on what the neutron star is doing, but there's maybe 2,000 that are known through various detection methods.
All right, on the left there.
I've heard Neil Turok on CBC radio say that there have been no fundamental discoveries of physics in the last 35 years. Is there any fundamental discovery that you can associate with this neutron star physics?
Yes. So let's see. I would say that neutron star merger is pretty remarkable because it tells us a lot about the galactic chemical evolution history, how the elements got made, and what the universe might look like far in the future. I think we often take a myopic view of what advances in theory might look like, and we assume that only advances of the order of totally new theories count. But even our understanding of pulsars and our understanding of the crust wasn't understood 20, 30 years ago. And now I can do a whole PhD thesis on it. So I think really great theoretical advances may have been made, even if they're not, the next general relativity. I'm sorry I couldn't answer that more specifically. I mean, so many things come to mind.
Yep.
Yes, according to this theory, what does the future look like if all these mergers continue to evolve down into these black holes? We've never seen one where there's still some doubt as to whether they do actually exist. But if everything evolves down into black holes, the entire universe will disappear.
That is a great question. The question is, what does the universe look like in the far future? Does it all end as black holes? That is a question that depends on how matter behaves. So if you took a proton and just set it out in deep space for trillions and trillions of years, does the proton do anything? It's possible that everything does just end up as black holes. Not all matter will, of course, end up as neutron stars and neutron stars merging with each other. That only happens under specific circumstances. But many cosmological theories, based on what we know to the best of our knowledge today, suggests that it's just going to be black holes a few trillion years in the future.
All right, yes, just behind them.
Every time we hear about neutrinos, we're told that the entire Earth is practically transparent to the neutrinos. Is a neutron star transparent to neutrinos?
It depends when you look at it. When the supernova first goes off, it can be opaque. And that traps neutrinos and helps to provide heating to blow off those outer layers in the supernova. As the neutron star or proto-neutron star cools off and eventually the crust freezes and all of these neat things happen, it will become transparent and it will just behave like a neutrino light bulb that just freely streams neutrinos out and radiates neutrinos. And that is one of the motivations for doing neutrino physics on Earth, is to better understand how neutrinos will behave and drive supernova explosions and what that might mean for the evolution of the elements in the universe. And so I'll just say sort of it's an open question, how neutrinos interact with matter.
All right, Brian there.
How many flavors of neutrinos does the creation of a neutron star inject?
It should create or radiate in all three flavors. I'm not a supernova person, and maybe the tau neutrinos might be in a smaller dose or be less considered. Treating neutrinos is very difficult in supernova theory, and a lot of people just work with one for practical purposes. And I'm also not a supernova theorist, but that is a very good question.
All right, we'll do two more. Just right there.
I would like to ask if the matter become what they call it the black hole. If the matter become a black hole, could that black hole turn into something in another matter that will come like a cycle again?
The question, as I think I might have understood it, is does matter going into a black hole or forming a black hole do something else beyond just be a black hole? Yes. That is a very good question that many people who are much better general relativity theorists than I have spent a long time working on, Stephen Hawking among them, and there is no clear answer on this because black holes contain something of a divide by zero error. Some ways, if you squint and massage the equations in a right way, the formation of black holes is a bit like a Big Bang in another universe. And there are these models of universes consisting of black holes and Big Bangs kind of all the way down. But it's not understood, and no one actually knows the answer to that. But I am confident that if you try to go into a black hole, you will only end up dead. Even if interesting physics may be happening in a multiverse.
All right, so we'll field one more question, and then I'm sure Dr. Kaplan.
And I'll be around for a few more.
Yes.
Can you elaborate on Magnetars? I read about it long ago.
Yes. So the question was Magnetars ? So I will just say that what you should know about magnetars really just comes from this right here. So if you take the magnetic field of a star before a supernova and then you sort of squeeze all the magnetic field lines together in the neutron star, you make something which has a magnetic field of 10 to the 13 to 10 to the 15 Gauss. I know that probably doesn't mean much, but that's just sort of the measure of having a really, really, really big magnetic field. And so for the first million years or so after the supernova, they have these enormous, enormous magnetic fields, which Those are reservoirs of magnetic energy which could power flares and outbursts, maybe fast radio bursts, which is what Vicky Caspi is working on observing and detecting, the woman who is featured in the video during the break. And that's basically everything there is to know about magnetars. They are neutron stars with enormously strong magnetic fields, and we're trying to understand as a field why those magnetic fields decay away in old neutron stars, and what kind of cool bumps in the night they might be making. So thank you very much for your attention. I really appreciate the invitation. It has been a pleasure being here, and I will be happy to take questions afterward.
All right, there we go. All right. Thank you. Thank you again, Dr. Kaplan. That was a fascinating talk. FLO star parties for members only. The next one is March 9th. I believe that is next weekend. Is that true? Let's hope for some clear skies and decent weather and no more snow. I've got my fingers crossed for no more snow. Although I probably just jinxed it. Damn it. Stell's pick of the month out of the Stanmont Library is Empires of the Stars by Arthur I. Miller. So be sure to pop into the back there to take that book home. Here are some of the folks that help run the club. Thank you for all your hard work. Come on. As always, our meetings are recorded, and you can view them from our website at ottawa.rasc.ca. We had 104 in attendance, so thank you for coming, and thank you to all the speakers and organizers, and to the museum as well for hosting us. Our post-meeting meeting will happen at Grace O'Malley's just on Ogilvie Road off the Aviation Parkway, so we can grab some snacks, drinks, and some chat. Our next meeting is the 5th of April, same bat time, same bat place. So if you have any ideas for talks or observations, be sure to submit them to me at meetingchair@ottawa.rac.ca. Membership benefits: if you join the club, you get access to the Ted Bean Loan Library, where you can borrow a piece of astronomical equipment, be it telescopes or binoculars, etc. You get access to the Stanmont Library to get some wonderful astronomy literature, and access to the Fred Lossing Observatory. You also get these wonderful publications: Sky News, the journal published by the Royal Astronomical Society, and the Observer's Handbook, as well as Astronauts. And this slide is a lie. We don't really have very many door prizes this month, so we're just going to skip it, and we'll save these ones for next month.